All right, welcome. This is a cross-industry benchmarking tutorial for distributed LLM inference on Kubernetes. Oh, well, I guess I can introduce myself first. I'm Samuel Monson. I'm a software engineer at RedHat focused on performance and scale at AI platforms. As part of my work, I maintain GuideLLM, which is a load testing tool for LLMs.
Hi, everyone. I'm Ganesh. I am software engineering manager at NVIDIA, leading the performance benchmarking tooling effort for NVIDIA AI Dynamo.
Hi, everyone. My name is Chen. I'm part of IBM Research, a software engineer, working on benchmarking LLMD.
Hi, everyone. I'm Jason Kramberger. I'm a software engineer for Google Kubernetes engine, and I am the maintainer of inference-perf, which is a benchmarking tool from the Kubernetes working group serving.
Hi, everyone. I'm Junchen Jiang. I'm an associate professor at U Chicago. I also lead the research team who created the LMCache project, and also I'm co-founder of TensorMesh, which built products on top of LMCache project.
This is a pretty broad talk. We'll be going over a lot of different topics. At various points, there'll be a QR code in the corner. They indicate some supplemental materials, just in case you're interested in trying any of the scenarios at home, assuming you have a multi-million-dollar GPU machine in your basement at home. We'll start with some background, get into the details of distributed inference, move into some use case scenarios, and then kind of close out with some challenges, limitations, and next steps. Let's start by defining the problem we are aiming to solve. We're going to make the assumption that your hardware is already fixed. You've already acquired or allocated a set of hardware for this project. Thus, we'll be attempting to find an optimal deployment strategy given your set of hardware. For a base case, let's consider just a simple single pod monolithic application deployment. In this case, this is our AI model server. We can scale this up the same way we'd scale any basic Kubernetes workload. Scaling out involves more pods. Scaling up requires getting more hardware to each pod. In performance testing, our goal is to optimize the trade-off between throughput, latency, and cost. Cost mainly boils down to the hardware. Since we eliminated that variable in our problem statement, we can kind of focus on just throughput and latency. LLM Inference is basically a traditional HTTP client-server flow. You ask the LLM a question, it returns you a response. You can measure the response time as request latency, the throughput as the number of requests you're sending. However, where LLMs differ from a traditional client-server flow is that the response is variable and depends on what the model decides to respond with. So there's a couple better ways we can break down the requests and responses, namely by LLM tokens. We can define multiple request latency metrics. The two most common industry metrics you'll see are time to first token, which is the time it takes to for the LLM to send back its first token, and inter-token latency, which is the mean time between every subsequent token after the first. You can also quantify throughput as tokens per second rather than requests per second. This gives us a better overall metric that works across different request and response lengths. Oh, there's the flow for a streaming request that does per token. Along with these metrics, we need a load to drive our benchmark. The simplest way is to send multiple requests to a server in synchronous fashion, one at a time. The next step up from that is concurrent benchmarking. This involves streams of multiple streams of synchronous requests running in parallel. Alternatively, we can try to emulate user request patterns using constant requests per second or some distribution over time. A final option, which is not shown here, is to trace a real-world workload and then replay those requests to the server. Over time, the industry has developed a variety of tools to drive AI load testing. Many of the presenters here are involved with the development of such tools. The ones you'll see in this presentation are inference-perf from the Kubernetes working group serving, GuideLLM from RedHat and NeuralMagic, AIperf from NVIDIA, and the vLLM benchmarking suite, which is a part of the vLLM model server. Using one of these tools, you can start to quantify your system's performance and make configuration comparisons. What you're looking for kind of depends on your use case. If your goal is to peak find peak reasonable throughput, look for the inflection point where your latency grows faster than your throughput, or to find a fixed load given some latency metrics objectives. With these rules, you're now kind of equipped to run some basic comparisons across different deployment options and find the optimal configuration. After spending some time tuning every knob you can find on your model server and your deployment config, you'll find there's some downsides of traditional model server deployments. At large scale, there's a lot of duplicate effort happening. You might get similar requests or responses, and scaling out in a simple deployment fashion doesn't really give you any shared caching. There's limited ability to tune your deployment for your workload. Specifically in model serving, you have a prefilled stage, which is processing the initial request approximately, and a decode stage, which involves processing every token after that. Sometimes you want to do more of one and less of the other. You have a limited ability to manage that trade-off with a simple deployment. If you have a very large, powerful model and that doesn't fit onto one node, you must have some mechanism distributing your workload across multiple machines. Luckily, the industry has come up with a solution for all these problems, which we call distributed inference. Distributed inference can split different stages of the inference pipeline into several components and implement shared caching mechanisms. In this talk, we'll look at two different distributed inference stacks, LMD, which is from a large consortium including RedHat, Google, IBM, et cetera, and NVIDIA Dynamo from NVIDIA. So now I'll hand it over to Jing, who will introduce us to LMD and LMBenchmark.
Thanks, Sam. So first, before going to all of the inferencing stack solutions that we have today, I want to first just describe all of the tools that we have in open source relating to AI model serving and inference. So on the top level, we have the base model servers. So SGLang and vLLM are example of this. On top of that, we have inference optimization techniques. So LMCache, for example, is a library that optimizes KVCache management when it comes to inference serving. And taking the best of all worlds, we have inferencing stacks like LMD and NVIDIA Dynamo that provides a single entry point to deploying models and also configuring, for example, inference optimization techniques. And in order to validate the performance of these inferencing stacks or optimization techniques and also model servers, we need a flexible benchmarking toolkit. So today we'll demonstrate the usage of all of these tools. So we're going to talk through AIperf, GuideLLM, inference-perf, LMD, benchmark, and also vLLM benchmark. So I'm excited to show some of our demos today regarding that. So I'm sure all of you have already heard a lot about LMD throughout this entire conference, but just to dive deep into one of the inferencing stacks that we have available in open source, LMD is one that provides a Kubernetes native distributed inference for users. And so I want to also dive deeper into one of the problems that may arise for a platform engineer when it comes to doing LMD deployment. So here is the architecture diagram for LMD. As you can see, there are different components. So on the top level, when the client sends a request to the inference gateway, the inference scheduler, which is essentially the router, receives that request, and it's an extensive library of different algorithms that will have observability into the cluster. So it understands, the load, the KVCache state, the different vLLM variant pods that are in the cluster, and it makes that intelligent decisions by sending the request to a specific pod that will optimize performance. So when the vLLM pod receives that request, it might be set up in a distributed manner. So it might be specialized for a certain stage of that inference, and that is either prefill or decode, or it might be set up in some other variant. And so these pods might have some internal connection and networking between themselves for communication. And on the very bottom layer, of course, we have KVCache configuration also. So as you can see with all these different moving parts, One of the problems and questions that we may have is how does one configure such inferencing stacks so that it meets optimal performance? Because inferencing stacks like LMD contains components that are highly pluggable, and it's also very configurable. So just to summarize, it may have on the order of 100 parameters, and with more inferencing optimization techniques, this number is only going to increase. So the end user sort of has to make a decision on 2 different layers when it comes to adopting and deploying LMD into their environment. First is defining the application. So that includes defining the model that they might want to use for their application, understanding the workload. For example, that could include the type of requests that are coming in terms of input and output sequence length, in terms of request rate. And the user, the platform engineer, also has to make decision on the deployment level. So how do you configure vLLM? Do you do so in an aggregate setting, in a PD disaggregate setting? What is the GPU to use for that model? How do you configure parallelism? How do you configure KV-cache management? And so with all these different combinations of the application and the deployment, we may get different performance. So some of the metrics, again, that we care about are time to first token and throughput. And so with all of this, at the end, the platform engineer might have to rule out some of the configurations that don't meet your service level objectives. And so for the desired application, the platform engineer has to make decisions on how to define those metrics. So as you can see, this is really a major problem that's hindering the adoption of these inferencing stacks because we have all these different moving components, and it's really difficult to know how to configure them. So this is exactly why benchmarking is needed. We need some way to quantitatively be able to make decisions about what is the most optimal configuration for using an AI inferencing stack. So the current solution is LMBenchmark. It consists of 3 different work streams aimed at addressing some of the problems that I just talked about. So first is providing automation to benchmarking LMD under different configurations and being able to reproduce data so that other people can view the data and perhaps do the same for their cluster and for their environment. Second is actually publishing the data to the community. So currently we're doing so through the LMD blog articles and also through a community Google Drive. And this is really to drive collaboration with the open source community and also identify more diverse use cases for new benchmarking scenarios that we might want to target. And finally, we need some way of exploring that data. So LMBenchmark currently contains an experimental feature, the Configuration Explorer, which is aimed at helping the user identify the most optimal configuration of LMD based on the data that we have published publicly. So today we'll show you some demos on how this is done. Okay, so diving a little bit deeper into the first work stream, which is the automation piece, what does LMBenchmark provide you? So this includes the nitty-gritty details of, for example, setting up the cluster, installing all of the CRDs that are required, and also downloading model weights for reuse, because some of the models that we're interested in benchmarking will take a very long time to download the model weights. So we want to promote reuse as much as possible. Next, we want to actually deploy the LMD stack. So that includes deploying the gateway router, so that's the inference scheduler piece, deploying vLLM, so that includes configuring all of the arguments and environment variables for it, and setting up KV-cache management behind the scenes, and also along with some other types of configuration. So once we have a stack up and running, it's time to actually set up the workload generator part of it and actually send some traffic to the model servers. So again, LMBenchmark reuses some of the existing tools that we already have because we don't want to reinvent the wheels. Some of these tools are very sophisticated and it fits most of the GenAI use cases that we have identified so far. So that includes inference-perf, GuideLLM, and also LMBenchmark. So finally, it's time to clean up the cluster and maybe prepare the cluster so that it's ready for the next configuration that we might want to benchmark against. So as you can see, LMD Benchmark provides this end-to-end automation workflow so that we can test the performance of LMD under different configurations, be able to send different workload traffic to LLM and observe its performance patterns, and also identify patterns where performance really shines. So LMD Benchmark is really this toolkit that provides the end-to-end workflow for benchmarking and running configuration sweeps against LMD and also against different workload. So this cycle enables us to provide a unified experience for inference stack benchmarking. So next, I'm going to hand it back to Sam to show a quick demo of LMD in action.
Thanks, Jen. Like she said, we're just going to go over a quick tutorial of using LMD and LMD benchmark. I know. For our first run, we'll need to define a scenario, which is our config for the run. Scenarios are split into two pieces. The stand-up tear-down config, which configures the deployment of LMD, the run config, which handles the deployment of the test harness. We're mostly using the LMD benchmark defaults for this scenario, though an important part I'd like to highlight is the harness and workload configuration. Within LMD benchmark, each harness has a number of workloads defined. For instance, here, the workload we have specified for the scenario for instance, the workload we have specified in this scenario, the format of the workload is up to the underlying tool and harness integration. As a comparison, here's the same workload defined for the inference-perf harness. You can see that there are a lot of similar values defined for each data format, or in different data formats. Now we'll go just through a quick run through. I need to play this video. Yeah, I need to move it over. So here you'll see the stand-up phase of LMD benchmark. If we give it a second here, we're going to start setting up our cluster, ensuring all our CRDs that are deployed for LMD. Give that a second. Then we're just going to ensure some namespaces are set up. We're going to download our model to the cluster so that it's available when we start the model server. Give that a second. There we go. And then we're going to keep ensuring things are all set up and deployed. Then we're going to deploy the actual LMD deployment, which we'll walk through that here. We're basically applying a bunch of Helm files. And now we're waiting for all our LMD pods to be ready. They're ready now, and now we're just waiting for them to be checked. Everything got checked off here, and there we go. All steps complete, which means our LMD model server is deployed. Next, let's do, I can't read anything, can I? There it is. All right. Now we're going to do our actual benchmark. So we'll run our run script. This is just going to verify everything we deployed before is set up and detect all the endpoints for us. Then we'll launch our benchmark tool. We'll run it. We'll wait for, we'll wait for it to done. It's done. Now we're ready. This was a pretty simple benchmark, so it doesn't take that long. Usually these take hours. And finally, we are going to tear down our deployment now that we've tested all of these, or we've run our tests. So this is basically doing the first stage in reverse. We're cleaning everything up, deleting all of the Helm resources. Give it a second. And now the cleanup's complete. It'll leave some things around, like the actual namespaces, the PVCs. I think there's probably a force flag to get rid of all of that, but that's basically it. It's pretty simple. All right. All right, now we've gone through our benchmarks. Once the benchmark is done, you'll get a few files back. Each underlying harness will return its raw data, but additionally, you'll get back reports in a standardized format that has been processed by LMBenchmark. For example, for the run we just did, we have multiple stages at different driving rates. You'll see a file that looks something like this, which will give you your latency and throughput metrics, some request statistics, the overall time of your benchmark, and other information like the arguments you specified in your deployment config. We can take this a little further by adding to what's known in LMBenchmark as an experiment. This will override specific parameters in your scenario to stand up different versions of your stack. This lets you tweak knobs in every component so that you can run a cross-validation across multiple different deployments. An experiment's pretty simple to write. There are two sections, the setup section, which defines, like before, your deployment and teardown config, and your run section, your workload. These define what variables we want to adjust, and then define a treatment section, which goes through each value all your values for each variable. So this experiment goes through all possible combinations of prefill and decode with 2 GPUs. We're essentially starting with 1 replica of each, moving to 0 prefill, all decode, which is basically the equivalent to a single monolithic model server. And then testing either tensor parallelism, which is giving 1 model server multiple GPUs, or replicas, which is multiple pod copies of the model server. As for the run section, we are adjusting the prompt and output token lengths that we're testing against in our scenario. So we'll get multiple different runs of our benchmark across all of these different rates. Taking all that, you can pipe it into the full end-to-end script as an experiment, and you'll get a run across all the scenarios. Now I'm going to hand it off to Ganesh, who's going to do the Dynamo and prefill decode side of this.
Hi, everyone. NVIDIA introduced prefill disaggregation last GTC. Before NVIDIA introduced Dynamo, the North Star goal for AI factories today is to generate tokens, and there are millions of requests that come into an inference endpoint requesting millions of tokens as output. Traditionally, so LLM inference has 2 phases, prefill and decode. Traditionally, before NVIDIA introduced Dynamo, all of these was done on a single, both these prefill and decode stages were done on a single GPU, which was not an efficient utilization of GPU resources when you take a look at both the phases. Prefill is compute intensive and decode generate is memory bound. So Dynamo decided to implement these optimizations in LLM inference by splitting these 2 phases out. And as a result of this, by utilizing 2 GPUs, we were able to gain 6 times the throughput for the same workload. Dynamo has a tool called AI Configurator, which gives you, define your service level objectives and gives you the optimal number of prefill and decode generation for your workload, which will let you deploy with those number of prefill and decode workloads. So Dynamo just doesn't split workload, it thinks as well. What that means is, as your request comes in, it decides what number of prefill and decode worker needs to be present in your inference stack. What that means is, let's say if you are getting a lot, if your workload starts increasing, if your workload start receiving more summarization requests, which means you have a lot of prefill requests that are coming in, and your workers are doing prefill task more. NVIDIA Dynamo automatically scales up and down your number of prefill versus decode instance, and vice versa. If you are getting a lot of decode requests, like a chat requests that are spiking up, NVIDIA Dynamo will increase the number of decode workers as well. NVIDIA Dynamo also has KV-aware routing. What that means is it utilizes previously computed KV caches, which are present on the nodes, and routes the request to that particular node. What that means is it achieves 1.5 times more requests per second. This is prefill scaling up, scaling down prefill disaggregation nodes based on the requests that are coming in to your endpoint. Next, next Dynamo also has KVCache offloading to storage. What that means is it allows users to offload the pre-computed KVCache, thus reducing time to first token dramatically. Junchen is going to talk about KVCache offloading and with LMCache, and after that I'll talk about benchmarking and Dynamo for KV-aware routing.
Okay, thanks. All right, so I'm going to dive deep into the KVCache part of large language model inference systems. And first of all, congratulations. You're already halfway through this session. OK. So far, we talked about how to view distributed inference systems as a whole, as a black box end-to-end systems, LMD and Dynamo, among other projects. And we have been looking at this inference system as a whole, as an end-to-end black box. You throw requests in, you measure the delay of the system. And this is just to remind you guys, this is the way we're looking at it. There's a router that distributes requests to each individual inference engines. And there's the acceleration layer based on KVCache technologies, which I will talk about, behind these inference engines to speed up things. Now, what I'm going to talk about is why KV caching is so important. Okay, and I'm going to shamelessly reuse some of the slides I used yesterday in the AI Day workshop. If you're there, if you have been there, just ignore this. But KV cache is probably one of the most important technologies to speed up inference in the coming years. Okay, why I say this is because when applications become scale, when companies scale up their inference workload, there will always be, and there will be more and more situations where the same context will be used by multiple requests. The same context can be a code repository. The same context can be news documents. The same context can be images. The same context can be user chat history or shopping history. Or just prompt templates, maybe. And when you have requests coming to the systems that try to use similar or identical context, you will have a long context inference situation, because the model have to read the context, all these things I just talked about. They have to read the context, and so-called, what Ganesh talked about, the prefill phase. And prefilling is very slow. Now, here's just an animation. When a request comes in, and the model have to read the documents as the context to answer the query, and each time, the model has to do a long prefill phase. Now, in this case, they're using the same context, okay? And if you notice, there's this blue cube created in the process of model's prefill phase. And what that blue cube is, that is the KV cache. KV cache is model's memory about whatever tokens it has read in the context, in the process of this query. Now, one thing, like I said, in the real workload, there are a lot of shared context. You can imagine if one user asks model a question about a financial document, for example, chances are the same document will be used by the same user for other questions, and maybe even by other users for other questions. In those cases, the model's memory about this context, about this document, for example, will be embedded in that blue cube. By the way, the blue cube, I call it, it's called KVCache. KVCache is the sort of common memory data structure by any transformers these days. Whatever open weight transformers or closed weight transformers you heard about, they all use KVCache as temporary memory of its attention information. Essentially, it's understanding of the context. Now, that cube, as long as it's the same context being used repeatedly, that cube is reusable. And when you reuse that cube, the model can directly skip all this processing, all the prefill computation that has been, okay, so the animation is already done. But my point is that it's so fast, it beats me, right? It's so fast that the model doesn't have to prefill the context anymore. It just simply reused the cube. And the question now is, actually, the benefit is you just prefill any context once, and the KVCache produced internally by the model in the process of that prefill can be reused over and over. Now, of course, the system problem here is how do you quickly store, transfer, deliver these KVCaches across different engines. And of course, what I'm talking about is all these semantics need to be supported by the KV-caching layer of the model of the inference system. Traditionally, on the left, you can see models have its own GPU memory, and the KV-cache is created internally by the model, and the KV-cache is just stored there. What these modern inference systems does, including LMD, production stack, and Dynamo, is it enables the KV-cache to be stored in the local storage system, including CPU memory and disk, and it also allows KV-cache to be shared over the network between different engines. And of course, there's also situations where you need to share KV-cache in real time between two GPUs processing the same query, which is what Ganesh talked about, the PD disaggregation, prefill decoding disaggregation. But for all these reasons, you need to have a shared library that supports all these semantics, system-level semantics. GPU to GPU, GPU to CPU, CPU to CPU over network or storage backend. And this is what we usually called the KV-cache layer, the KV-caching layer. LMCache, which is the project we did. Mooncake is also another community project. These are all open source projects to support these functionalities. And supporting these functionalities are far more, it's easier said than done, okay? There are multiple technical challenges here. First of all, and this is why these libraries, people open sourcing these libraries are so valuable to the community because they solve these problems for you. Okay, first of all, KV caching layer, it doesn't exist in vacuum. It has to work closely with the inference systems, including especially the inference engines. And as you know, these days, inference engines themselves are hyper-optimized with all these kind of crazy optimizations like page attention and page memory. Okay, and also crazy dynamic batching or scheduling algorithms. And so it's very important that KV caching layer work smoothly with these engines. And very importantly, you need to make sure that the KV caching layer doesn't slow down the engines, because KV caching layer is strictly adding more I/O operations on top of whatever these engines are already doing. Okay, so making sure things work smoothly with the engines is very important. Secondly, it's not just a static problem. These engines themselves are evolving, right? They're new open weight model. On average, new open weight model, new major open weight model released every 5 days. And these engines are evolving at the same time. Now, the other thing is KV caching layer is a bridge between the engines and the storage system, all kind of storage systems. So the KV caching layer is also evolving with the ecosystem as well. So how do you make sure these two libraries can co-evolve at the same time? For example, in the case of LMCache, there is a standardized interface called KVCache connector used by all these projects as well to stabilize this interface between, or standardize the interface between engine and the KV caching layer, so the two parts can co-evolve together. Next, the KV caching layer also has to produce locational information for the whole system. For example, the router to decide and to decide which KV cache is located in which server, right? So that the router, as Jason will talk about later, can decide can choose smartly which server or which engine it should redirect the request to, so the KV cache is available locally. Now, for all these challenges, good news for the community is there are open source projects such as LMCache and Mooncake to solve these problems. And these libraries are integrated to various extent with the inference engine projects and also with the inference stack project, distributed inference framework projects. And these projects, I'll be honest, there are issues when people run them together, but it's a fast evolving space. And as we will see later, the performance is also fantastic. And a lot of these projects, by the way, a lot of these projects use LMCache as well. So some of the results, I won't show any results here, but some of the benchmark results will be based on these open source projects as well. So now let's go back to showing more results.
So as I was talking about KV-aware routing in Dynamo, I am going to benchmark that as a baseline being non-KV-aware routing versus KV-aware routing. So the tool that we are using to benchmark Dynamo deployment is AIperf. And this is the UI while it is benchmarking. It updates the benchmark progress and metrics real time. So on the right side, you'll see the metrics that it generates. It also generates reports and visualizations. Visualizations is that AIperf generates, which helps user to analyze their deployments, is shown here. Next is, one of the challenges to benchmark deployments is to have real-time traffic with user privacy. So what that means is collecting traces and encoding them in block hashes. A company that Junchen just mentioned, Mooncake, released traces, which represents real-time traffic to a system. So here, the block hashes that are color-coded in blue shows the repeat of the request, the overlap of the prefix that came to the system at various different times. So what that means is, with the system that has built-in KV-aware routing will outperform the system that has no KV-aware routing built in it. Next, this is the payload format of the Mooncake dataset. It has timestamp at which the request arrives to the system, input length, output sequence length, hash IDs. Hash IDs represents the actual payload that is sent to the system. So this is the AIperf benchmarking command line used to benchmark using Mooncake traffic. It is supported out of box in AIperf. So the baseline, as I mentioned, is without the smart router, AIperf as the client, and Dynamo endpoint. And the performant version is with the Dynamo smart router enabled deployment. So the screen is split in two halves. The left one is without smart router, and the right one is with Dynamo endpoint with smart router enabled. As the benchmark progresses, you'll see the AIperf dashboard that comes up. It shows real-time progress, logs, and the metrics that are being generated, that is being observed by AIperf, and gets updated real time. Once the benchmark is done, it will generate a summary in the console along with the artifacts in the files. So the right one with smart router is already done for that given trace, which already showed some performance benefits based on the time it got done. So that was the demo. And the results are, with smart router enabled, with KV-aware router enabled, you'll see 53% jump in time to first token and 35% higher throughput because of that optimization that was done in Dynamo. Next, I'll hand over to Jason for prefix-aware routing.
Everyone, a lot of listening, maybe a little moving. Hands up if you've got H100s ready to go for this next tutorial to run on. Really? We'll talk later then. Hands up if you want some H100s to run it on. Talk to Ganesh, he works for NVIDIA. All right, we're going to go through prefix cache-aware routing with LLMD and LLMBenchmark. We're going to go through the configuration of LLMD and the experiment design, and then we're going to show running and analyzing with LLMBenchmark. So I'd like to call out that inference-perf is the Kubernetes working group serving effort to standardize on benchmarking methodology and metrics. It's scalable to support large production inference workloads like LLMD. And it's the current default supported harness inside of LLMBenchmark. LLMBenchmark, Jing went through earlier, but it's basically a benchmarking suite to run any of these tools in order to produce unified benchmarking results. The inference scheduling or precise prefix cache-aware routing well-lit path inside of LLMD utilizes the Gateway API inference extension, which is a Kubernetes open source project, and specifically in my demo would be using the GKE inference gateway. But the goal here is to route traffic precisely off of the KV cache entries to reduce time to first token and maximize your KV cache hit rate. And that means that you get fewer cache misses and you reduce latency spikes and you have predictable scaling. So the experiment design here with a QR code that links to the LLMBenchmark repository with the exact configuration in which this benchmark was run to repeat. It's running LLMD in precise prefix cache-aware mode with Qwen332b on 8 total H100s, 4 instances of tensor parallelism size 2, and it's utilizing the GKE gateway provider. On the right here is the output of our kubectl get all, where we see the 4 decode instances at the top, the pods, as well as like the model download job. And the experiment design for inference-perf, we'll do some napkin math here, because deciding what you are going to input into your benchmark is probably one of the most important parts of your benchmark. In the Qwen332b setup, we have about 5K GPU blocks of 64 tokens per block, which means we have around 300,000 tokens per instance. And we have 4 instances here. We configure a data set where we're going to try and have much more KV cache with the distinct prefixes than any single instance can handle. So we select 128 prefixes, around 6K tokens each. That gives us a total of around 800,000 tokens, which is 63% of all 4 instances KV cache. Further here is the rest of the configuration for inference-perf, where you're able to select the rate you would like to run and the duration of each load stage, as well as the generation report config and the API and server config that's passed through with the LLMBenchmark script. So we'll skip a video, but here's a screen grab where the bottom left, we've got that same script output that we saw earlier with LLMBenchmark, the kubectl watch on the bottom right, and then the top is the log tailing from the inference-perf pod. So you've completed your benchmark, you've waited in between 1 and many hours, and you have your output directory structure that we've seen before, this time with inference-perf and each stage's individual detailed results that show rich metrics from normalized time per output token and inter-token latency and time to first token. And the inference-perf analysis module runs automatically with LMBenchmark, producing some graphs where we see here throughput versus the rate that we run on the bottom. And then also our expectation of having a lower time to first token across running. You can see the mean and median here, with the median being the lower line, staying pretty close to 0 as we increase load. So future improvements, inference-perf is about to release its 1.0 version. The QR code here links the repository. Inside of that will be trace replay and multi-turn data set, as well as concurrent load type. And I'll hand it over to Jing for prefill, decode, disag.
Okay, thanks, Jason. Okay, so again, I want to remind everyone sort of the central question that we're trying to answer here, which is how to best configure the AI inferencing stack so that it brings optimal performance. And so you have just seen some demos of how we've been doing this through LMBenchmark and how to run configuration sweeps for the inference scheduler part of LMD in general, and you've also seen how NVIDIA Dynamo is doing this through AIperf. And so right now I want to show a quick demo of how to configure the model server part of LMD, and so making that decision so that the configuration that we're interested in deploying LMD under meets performance needs. So again, because LMD is so highly configurable, we want to be able to answer this central question. So imagine that you're building a chatbot application, and the main goal of this chatbot is to do document summary. And so some of the metrics that you might care about include, throughput or TTFT. And so because from all of the demos that we have just showcased before, you already know how to configure the inference scheduler part of LMD. Now it's time to answer how do you configure vLLM so that it also brings optimal performance. And so again, do you do so in an aggregate setting? Do you do so using prefill, decode? At what point does PD not yield any performance improvements? So these are some of the questions that will arise, and this is exactly why we want to run a PD disaggregation experiment against LMD. So here is the QR code that you can use to get all of the details related to the next demos that I'm going to show. So I'll give everyone a little bit of time to scan that. Okay. So I just want to start off by showing you some of the results and walk through sort of step-by-step how we're able to get this. And again, this is not really about the results that we're showing here. It's not really about the data. It's more about the step-by-step process to get this result, to get to this chart that we see here, and to be able to surface some interesting information about LMD under different configurations. So let's say that we have the data here. What do you see? So this chart is plotting throughput per GPU against throughput per user. And so the solid lines represent aggregate LMD setup. The dotted lines represent disag. And you can see that this orange line sort of is shining from all the other configurations. This dotted orange line represents one prefill and one decode, where tensor parallelism is set to 8. And you can see that it really maximizes the metric on the y-axis and also on the x-axis compared to the other configuration. And this next chart shows how many configurations actually meet your SLO requirements. So imagine you do know the SLO requirements for this document summary application that we're building. Each data point on this graph represents one configuration and the results and the performance that we're getting from it. Right now, we're plotting we're plotting throughput per GPU against TTFT. And so all of the ones that are in black and in pink, I'm not really sure if you're able to see it, but but they are the configurations of LMD that represents the ones that meet SLO requirements. The pink ones are the most interesting because they are sort of at the forefront of the Pareto frontier, meaning they minimize TTFT and also maximize throughput. And we can't really improve any better without degrading the other metric. So those are the configurations that are most optimal from this data point chart that you see here. And so here is the scenario file that we use for LMBenchmark. This outlines all of the default parameters that we're setting for the experiment. So in particular, we're interested in comparing PD against aggregate vLLM setup. And so the parameters of interest here, that on the top, we see that we're setting model, we're setting the GPU to use. So those are the common parameters that we're setting for both PD and aggregate. In the middle, we're defining the parameters we're interested in sweeping over, so possibly changing the values of. And that includes one specific to prefill and also one specific to decode. So for example, prefill tensor parallelism and decode tensor parallelism. Those are some of the parameters that we might change when we're doing configuration sweeps. And on the bottom, we're defining which harness to use. So again, in LMBenchmark terms, that just means the workload generator. So previously, you've seen GuideLLM and inference-perf. Right now, we're using vLLM-benchmark and the random concurrent, which represents the experiment profile to the harness, is essentially the inputs to vLLM-benchmark. So you can see LMBenchmark is a very extensive and pluggable tool that reuses all of these upstream projects. So the harness profile on the right, you can see that we're fixing input token length to 10K and output to 1K, and we're using synthetically generated tokens. So this describes our scenario. Next, we can define our experiment. So the experiment allows us to iterate over different parameters and combinations of those parameters. So on the top, right, you see that we're iterating over different values of a prefill replica, of decode replica, and also over tensor parallelism. So the treatment list describes the combinations of those parameters. So the first item in that list, we can see that it means we want to deploy LMD such that it's one replica of prefill and one replica of decode, where TP is 8 for both prefill and decode. And that bottom, and so the last item on that list represents just a vLLM vanilla deployment. So that's the aggregate setup. So one replica of that, where TP is 8. And so that treatment list really describes the combinations of aggregate LMD and also disaggregate. We can also override different parameters for the workload that we're using. So you can see that on the bottom, we're overriding values of concurrency and also number of prompts for the vLLM-benchmark workload generator. So that list describes increasing concurrency and also the number of prompts sent to the model server. So with that, we're able to surface some very interesting data. And so taking all of these input, we can automate a full end-to-end workload experiment. And the output, again, is a set of standardized benchmarking reports. So that captures the LMD stack configuration, which includes the exact arguments used to set up vLLM, whether or not it's an aggregate or disaggregate setup. Also parameters to configuring the inference scheduler, so anything you can imagine there. It also captures the configuration for the workloads. So this is allowing users to understand what traffic was sent to the model servers and be able to reproduce the data in their own environment. And finally, we're capturing a list of performance metrics. So that includes TTFT, ITL, latency, et cetera. And so the reason why a sort of standardized common benchmarking report is needed is because, as you can see, LMBenchmark reuses all of these amazing upstream projects, but we need a way to communicate between all of these different formats that each harness is using. And so this common benchmarking report allows us to view the data regardless of the workload that is being used. And so we're able to surface very insightful conclusions from the data. So So the next part, I want to show a demo of the Config Explorer, which is the experimental feature we're incubating as part of LMBenchmark. So the Config Explorer actually uses the report schema that we use, that I described in the previous section. And so the data that I'm showing here is available through the LMD community Google Drive. You can use the QR code on the upper left for that. And the video to the Config Explorer is also on the upper right. Okay, that's amazing. I can actually show a live demo. I thought I had to show a video. Okay, so here is the UI for the Config Explorer of LMD. The first part is to download the data that you get from the LMBenchmark community Google Drive, or if you if you're able to like actually run the experiment, you will also have those files locally. And so that would be the first step. So that's something that you would input to the Config Explorer. So let me just grab that. So I have all of my data here. So once we import that, this actually goes through finding all of the YAML files. So that is the standardized benchmarking report. And so all of the data in a data frame looks like this. So you can see that it captures information about the vLLM deployment, whether or not it was deployed in an aggregate or disaggregate setup. It includes capturing configurations for the inference scheduler. So that's what you see here. And it also includes all of these performance metrics that we're interested in exploring. So LMD, so this Config Explorer actually dissects the data on a single model level. So again, as we said before, if we're interested in building a document summary tool, we're able to define our application this way. And so here is how you would give a higher level representation of all of the parameters you're interested in filtering. So document summary. In this tool, you're probably interested in how the input sequence length and also the output sequence length. And for chatbot, that might be different, right? Because for chatbot, you might care about the prefix hit rate and also concurrency. So for each application, there's a different set of metrics you're interested in filtering for. And so we can already see, it's able to provide you on the right-hand side some interesting graphs, and you're able to customize them to surface different information, and it provides you that real-time update. So this chart, if you remember from before, we've already seen. On this tab, we're able to examine the optimal configuration for all of the data we have. And so if I'm interested in restricting my SLO requirements, I might want to add a new one. So for example, let's do inter-token latency. So as you can see, if we're setting this requirement to 0, none of the configurations would meet your SLO requirements. It's impossible to meet this. But you can change these values, and it's able to do some more filtering and show you all of the optimal configurations that would meet your SLO requirement. So again, this is the Config Explorer, which is the experimental feature incubating as part of LMBenchmark. We're going to improve based on community feedback. So excited to show you this. And so that would be it for LMBenchmark. I hope you're able to draw some useful insights about it, and looking for your contribution. I'm going to hand it back to Jason to do a final wrap-up of what we have shown you today.
Cool. Thank you, Jing. All right, for closing, we just wanted to highlight what the current state is and what the desired state is from our point of view now. We have these flexible benchmarking tools that we're relying on, over a wide array of them, to tackle some of these new state-of-the-art inference deployments and orchestration techniques. And the desired state is really a standardized version of this, both at metric level, but also like definition of use cases, and to really help the apples-to-apples comparison across all of these different parameters. More intelligent way to benchmark, and then more coverage and analysis over the newer state-of-the-art deployments like disaggregation, et cetera. So please get involved, reach out to us, contribute to open source. Here's a whole drop of QR codes for all of the stuff that we mentioned, and we got some negative minutes for questions. If not, please reach out to us in the hallway and have a conversation. Thank you, everyone. Yeah, you got 5. You got to zoom in on every single one if you want it, you know? If we do have time for a question, anyone?
Awesome. Like you can see from the QR codes, there are a bunch of projects that are doing benchmarking. Why? As in, why can't we have one project? I like the LLMD benchmark project. I think it has a lot of potential. But in my last 6 to 7 months, there is inference-perf, there is GenAIperf from NVIDIA, there is AIperf from Dynamo project. RedHat has, with the neural magic, GuideLLM. I mean, I think we should get to a point where we can converge on one thing, because a lot of projects, or a lot of what I've seen, the way benchmarks are designed, sometimes they make that one particular project look good. So if we standardize on one thing, I think people have one thing to go to and run that one thing against whatever they want to run against, and get the same data and have the same way of visualizing it. I think we have all of us here on the stage. I think it's the right time to focus on one and maybe make it better.
I can take that. That's a great question. The answer to that question is we have started that conversation. We'll keep you updated to the North Star goal that you just mentioned. Yeah.
I'll add some credit towards a lot of the work has been along alignment with just methodologies and standardization of metrics. I think the tools are kind of just an implementation detail, and like Ganesh said, those conversations are happening, and convergence is definitely the desired state.
Yeah, I think I also, sorry.
One final bit. There we go. One final bit. I think that probably is going to happen eventually. At the moment, a lot of us met for the first time for this talk. So we're really in the early stages of kind of consolidating on a direction. Jason said, it's kind of at the moment, there's no one good way, so we've all kind of approached it in different ways. All the tools have similar features, but the features are implemented slightly differently. Eventually, yes, we will probably push that direction. I think LMBenchmark is kind of a first step, where it's just you get used to driving all the tools the same way and getting all the output the same way, but we'll see where it goes from there.
Yeah, I think I also want to add to that. So, I mean, thanks to KubeCon, we're able to show you this presentation and this talk, and I think that's also the first initial step we're starting to think about in terms of convergence. And again, LMBenchmark, instead of creating its own benchmarking tool, we're able to reuse all of these upstream projects. And so, again, that is another initial step that we're taking. So definitely we'll keep the community updated on that.
Just a little switch, turn it the other. Yeah.
There we go. Yeah, again, great talk. Really learned a lot. I think someone kind of made a joke at the beginning, but just run your H100 cluster. For those who are GPU poor, is this kind of is there any way what's the takeaway for us? I was what would you say for someone who's this is really cool, I also maybe don't have an H100. How do I actually contribute to this? And if I'm interested in LLM performance, where do you kind of see that going? What's the for Kubernetes originally, right? We got K3s, and also we can run this on a Raspberry Pi. Where are we kind of going with this?
Yeah, I'll just start off. I'll take ownership for that terrible joke. If it's any consolidation, I actually used A100s, which nobody cares about anymore. You can get them for free. Not really, but. We wanted to actually have something prepared, and there is some resources out there in the community in LMBenchmark and in everything else where there's simulation versions of the actual model server, so you can actually try them at home. There's CPU implementations as well, although obviously you're pretty limited in model size and scope. We just weren't able to prepare a demo for that during this talk. We plan to actually follow up with that and kind of have some resources there. But H100s isn't a hard requirement. You could probably run this on L40s, you run it in the cloud, you can figure out some smaller scale deployment. It's just that's really LMD and Dynamo are trying to push performance as hard as possible, so you kind of start at a higher baseline. Yeah, I don't know, someone else?
I'll just add the LLMD well-lit path that I benchmarked in its official definition is on Qwen 0.6b. So, smaller model, maybe more approachable anyways.
If you don't want to run benchmarks, there are simulated results from AI Configurator. It's a tool in Dynamo to deploy our prefill and decode, number of prefill and decode instances. It has done the computations for you on a given hardware, which gives you the deployable config for your use case, if you don't want to run actual benchmarks.
Yeah, I think adding on to that, I feel it's important to sort of separate actually running the benchmark from providing the toolkit, being able to run that benchmark. And so GuideLLM, inference-perf, they're all workload generators to enable you to run benchmark, and actually running the benchmark and producing results and publishing to the community. That would be the subsequent step. So I don't think in terms of contribution, it really hinders you from contributing to these upstream projects.
Hello, from IBM Research here. Is there any way to get involved into these kind of conversations? Because we have been working for years on exploring configuration spaces and optimizing them. We have a tool that's working already for vLLM performance to choose the optimal configuration to deploy. We have benchmarks for geospatial models. We have benchmarks for large language models. So we have all the plumbing. We have an open source tool that's called ADO. You can find it on GitHub, IBM/ADO. So everybody's, please have a look. Because really this resonates, and it's +1 to whatever, to the person before. We really need to standardize, and we have this idea of pluggable actuators that can explore these spaces. We have tools for Pareto set analysis, trimming of configuration spaces, working on important features. So yeah, these things would really work well together. And I think if you provide any guidance on how to collaborate on more on these things, because we have tools for you.
I will just respond with, please come to both the inference-perf working group serving meetings that are open source, as well as the LLMD benchmark meetings, and let's have that conversation. All contributions, everything is welcome.
And for Dynamo, it's open source as well. Please feel free to reach out and have a discussion on the Dynamo GitHub page.
Thanks. I'm curious if any of you are using K-Agent to run your tools?
One more time. We're on the wrong side of the speakers.
Oh, sorry. Yeah, I'm curious if any of you are using Claude Code or K-Agent to run your tools.
K-Agent, is that what you said?
Yeah. Do you know what that is? Okay, it's
Probably not, but
probably
doesn't-
not
that
because you don't
doesn't-
know what it is,
no.
or you haven't tried yet?
from the LMBenchmark perspective, we're not using agents or K-agent to run any of the benchmark, but I feel like that doesn't rule out the possibility for a future for that to be part of the future roadmap, using agents to run in benchmarks.
I mean, one response to the there are too many tools might be just run them with your agent.
I'd love to have a longer conversation with you about this, because this is an area that I've explored a little bit but has not made it to open source. So I think it's a great point.
Okay, full disclosure, I work with Ganesh, and I'm running Claude Code over there and his tools, so it's a pretty good combination.
Sleeper agent. You're going to help us get us more GPUs to benchmark, right?
Yeah.
Hi, thank you for the talk. So I have a few questions regarding KVCache. So my first question is, how long is data typically retained in the KVCache during distributed LLM inference?
I think.
Able to hear you. Can you please repeat once again a bit louder?
I'm sorry. So how long is data typically retained in the KVCache during distributed LLM inference? So I think it's by, yes.
Sorry, is that, are you asking how long usually the KVCache need to stay in the system?
Yes.
Of course, this is very, very workload dependent, right? Chat applications, for example, the KVCache need to stay there until the next question of the same user comes, because the KVCache is about user's chat history. No one can predict when the next query from the user will come, right? And so typically, what really matters is not set a time to live threshold, to be honest, because this is typical caching system, right? So every item will have a time to live, but that's just a maximum time to live. And what really matters is, do you have enough fast memory to keep all the hot stuff, right? Hot items. And by hot items, I mean items that will be repeatedly queried. And what, at least from our experience, from LMCache deployment experiences, typically real use cases will have a pretty stable workload distribution, meaning if you study past traffic and set the CPU memory, for example, let's assume CPU memory is the fast storage for KVCache. If you set the CPU memory threshold at a certain level, you can study from past traffic how much is the hit rate of KVCache. That hit rate is pretty much predictable of the future hit rate, and when you set the same CPU memory size for KVCache. Now, what's interesting is this is only something you can do when the workload stabilizes, right? When you have a large enough application, or you have an application with large enough user base, and you can study things from past to predict future. Very often, when companies are small, let's say, or business has not scaled yet, users are largely experimenting the LLM systems, and at that point, the history information is not very useful. So this is a kind of chicken egg problem. People used to have, I mean, the first phase of all the development is experimental. It's hard to do this kind of study until you hit stable workloads, and that is a challenge. I'll be honest, that's a challenge.
Thank you so much.
Hi, thank you for a great talk. We've looked at some of the benchmarking tools and the config explorer, and there's many ways to do experiments and compare different parameters. So my question is, do you have any interesting insights into some of the results of these experiments and some of the maybe unusual or unexpected configs that result in certain outcomes?
So are you asking being able to pick out the abnormal configuration?
Sorry?
Do you mean some of the outliers in the data?
Yeah, exactly.
Yeah, that I think would definitely be a good next step. So as you can see, the config explorer is still in sort of the development experimental stage. So that I can definitely see being another use case for the config explorer. So if that's something that the community is interested in, we're definitely will be able to explore that deeper. So I also want to mention that the LMBenchmark community meetings happen on Tuesdays. Bi-weekly at 1 p.m. Eastern time. So that's where you can, get involved with all these discussions about the config explorer, about LMBenchmark in general. So if that's a use case that you're interested in, definitely come to our community meeting. Let's also just connect offline after this talk.
I'll kind of add something to that, because I think if you're asking for specific results, the defaults are pretty optimized for general everything. But if you want anything more optimized than that, you really need a use case. You need your use case, you need basically the whole workload known in advance, and then you can kind of test against that.
Yeah, see, one thing that stood out to me was the example with tensor parallelism of 8 on one replica versus TP4 with 2 replicas. And TP8 on one replica performed better. Is that just because GPU proximity, they're all on a single node? Or things like that, that's what's super interesting to me.
I'll add to that. It's as you expand the config space and the deployments become less and less straightforward, the more situations you run into like that, where you call up your infranet engineers and ask why 2 GPUs aren't faster between each other. So it opens up exploration of those types of findings that we've observed.
Yeah, thank you so much.
I've seen I've tried Dynamo and LLMD both. Is there a future where both of these kind of merge or work closer together? And also, what's the governance future for each of the projects?
We'll answer that similarly to the other question. There's conversations about convergence and shared methodologies and ideologies between both, and it's really early days. So I think we'll see a lot of evolution in the short term.
Did you mention GenAIperf?
No, I meant Dynamo
I see.
and LLMD.
Yeah. We are definitely having that conversation as you are speaking. We'll keep the community updated with the progress. Please attend those meetings. You'll get the real-time update with that, what's going on. Thanks.
Right. I mean, I see a lot of good efforts happening in both sides. It would be really great if we could have it one place and make one single, I guess. Yeah. And I feel like these projects could be one of those things which can make it really easy for users to be yeah, here is my model, go figure out how to deploy it. Whatever is the most optimal way to deploy it. Because right now there's a lot of knowledge somebody has to carry. Oh, I have this GPU, it has so much memory. If there is, if they have NVLink or RDMA backed or whatever, it's too much to think about right now. The question asked before, what's the optimal way to do deployments and things like that. So I guess these could be the North Star for these projects. Yeah. Thank you.
Thank you. And thank you, everyone.
Thank you. Thank you, everyone.